In multivariable calculus, calculating areas of complex shapes is a fundamental skill. Today, we will use double integrals to find the exact area of a polar cardioid, a heart-shaped curve defined by the equation r equals a times 1 plus cosine theta. While single integrals can solve this, double integrals provide a robust framework for understanding area in polar coordinates. By integrating the constant function 1 over the region, we can determine the total space enclosed by this unique geometric boundary. In polar double integrals, the differential area element dA is not simply drd. Because the arc length increases as we move further from the origin, we must include a factor of r, making our area element a drd. To set our integration limits, we look at the radial direction. For any given angle theta, the region starts at the origin where r is 0 and extends outward until it hits the boundary of the cardioid, defined by our function. Next, we determine the angular bounds. To trace the entire cardioid exactly once, we must sweep our angle from 0 all the way to 2 pi. This covers the top and bottom halves of the heart shape completely. Combining our bounds and our area element, we arrive at this double integral. Notice how the inner integral handles the radial distance, while the outer integral sums these radial slices across the entire range of angles. We begin by integrating r with respect to r. This gives us 1/2 r squared. Evaluating this from 0 to our boundary function, we get 1/2 times the square of the quantity a times 1 plus cosine theta. To make the outer integral manageable, we expand the squared term. This results in 3 distinct parts, 1, 2 cosine theta, and cosine squared theta. We can pull the constant a squared over 2 outside the integral. The term cosine squared requires a power reduction identity. We replace it with the quantity 1 plus cosine of 2 theta, all divided by 2. This substitution is key to integrating trigonometric powers easily. Now we combine the constant terms. 1 plus 1/2 gives us 3 halves. Our integrand is now a sum of 3 simple terms that we can integrate individually with respect to theta. Integrating term by term, 3 halves becomes 3 halves theta, 2 cosine theta becomes 2 sine theta, and 1/2 cosine 2 theta becomes 1/4 sine 2 theta. We are now ready to evaluate at the limits. When we plug in our bounds, a beautiful simplification occurs. Sine of 2 pi, 4 pi, and 0 are all 0. This means the periodic parts of the curve cancel out over the full rotation, leaving only the linear theta term. Multiplying 1/2 a squared by 3 pi, we find the final area. The total area enclosed by a cardioid with parameter is exactly 3 halves pi a squared. This is 1.5 times the area of a circle with radius a. It helps to visualize the result. Since the cardioid extends out to 2a but pinches at the origin, its area being 50% larger than a circle of radius a is a very intuitive conclusion. To recap, always start by identifying your radial and angular bounds, remember the extra art in your area element, and use trigonometric identities to simplify the integration of squared terms. Try a quick calculation. If the parameter is 2, we square it to get 4, multiply by 3 halves, and the area becomes 6 pi. Applying the formula is straightforward once you have derived it. You have now mastered calculating the area of a cardioid using double integrals. This technique is a powerful tool for solving many problems in physics and engineering. Thank you for watching. Generated by Vision Solve AI.